welcome to Physics 11 on this kind of rainy and gross looking Tuesday afternoon. This is your second last lesson in Physics 11.
What? Why do you not want to do Physics 12? You will.
I'm going to do attendance real quick, and then I didn't do attendance in any of my blocks today. So let's just do this real quick. Ahmad's here. Harshan, you back there? Yeah, Harshan's back there. Manuel, not. Fine, I'll do a question. Your attendance question for today is this. Let's go this page. Okay, here is your attendance question for today. What is one personal rule you have for yourself that you will never break? Actually, I shouldn't say it that way. What is a personal rule you currently have for yourself? Give me one. I had a few growing up. I had a few that I just established for myself.
Give us a minute to think.
That is one that you could apply to yourself if you would like.
Wait, what?
There, I'll pause this. Hold on one second. Here we go. Questions about anything I assigned yesterday, Naya?
I'll let you assign.
Questions about anything, or anything from physics class yesterday?
You didn't assign it, but number 2.
Number 2. A hiker shouts toward a cliff 685 meters away. The echo is heard 4 seconds later. That one? Okay. Or this number 2. Oh, no, I didn't assign it, so it must be that number 2. What is the speed of the sound in the hiker's voice in air? The trick with 2 is to recognize that an echo is the sound there and then back. So you have to double the distance to get and the time.
I got it.
That's going to give you A, and then the rest follows easy because it goes there and back. Okay. Anybody other questions about what we covered yesterday? Going once, twice, thrice, sold. Cool. Let's talk about some cool little phenomena that happen with waves. So the first set we're going to talk about, we're actually not going to talk, this will come later, scribble out diffraction, we're going to, and in interference, scribble out interference and diffraction. We'll talk about those later. Today we're going to talk about reflection and refraction. I was supposed to pull up some videos, and I totally forgot, so give me a sec here. Okay. So, here we go. So, reflection of water waves. Water waves are the example we're going to work on here for a little bit. Water waves and light waves are actually fairly similar in some of this regard. Due to the lack of time we have and the amount of lab equipment we don't have for this particular unit, I'm just going to give you a bunch of these things instead of spending time, exploring them and figuring it all out for fun. We don't have a lot of time, don't have a lot of the equipment, so we're just going to talk about it. So when waves hit a barrier, one of the things that happens is they are reflected, believe it or not. We see this with sound waves all the time. Just experiencing an echo is all about waves being reflected. In this case of an echo, it's coming straight back at you. In the case of like Riley and Lainey in the hallway right now, I don't have line of sight on them. I can't see them where they're sitting, but they could hear me if I yelled at them. And well, why is that? Because sound waves just bounce around an area. Going out that door, they'd bounce around the corner. If I yelled loud enough, they would hear me. Hey, Lainey! Hey, Lainey! See? There she is. Thank you. Manuel, see? Look. You heard me, yes?
I do have ears. Yeah.
Perfect. More importantly, it's not just about you having ears. It's about the fact that I couldn't see you. There was no direct sight to you, and yet my voice bounced its way around and out the door to you. Thank you. That was it. They didn't believe I could do it. So when you've got, water waves are very similar. Yeah, hilarious, Tristan. That's okay. Water waves are very similar. Sound waves, water waves operate. Light waves, same idea. The angle of the language here is the angle of incidence This is the angle of something coming in. Is equal to the angle of reflection. So I drew this yesterday, and I'm going to have you draw it here as best you can. If you don't have a protractor, this is going to be real tricky. The way this is angled, these are the incident waves. The incident waves are the ones that are coming into the barrier. They're coming in at 30 degrees, and what's actually going to happen is they bounce off at 30 degrees. Water waves do this, sound waves do this, light waves do this. Same thing down here. Waves that come in at 75 degrees are going to leave at 75 degrees. The really easy one is the waves that go in at 90 come back at you at 90. You hit the wall, they come straight back. And that is just a property of waves. It's not particularly profound. This isn't the fact that the angle that they come in at is equal to the angle that they leave at isn't necessarily obvious or straightforward, but it's true. So that's kind of cool and kind of useful. And if you've got a protractor out, or at the very least take a picture of this, and you can draw it for yourself a little bit later. We used to have a math set of protractors, and I couldn't find them, so my apologies there. Take a picture of that, and I'll have you add that later. Oh, sorry. Well, then someone take a picture and airdrop it to Khalil. Sure, yeah, selfie while you're at it. Okay, here we go. Fifth page. Light is similar. When light reflects off of a mirror, the angle of incidence is equal to the angle of reflection as well. The interesting thing with mirrors is that they're not all flat. Thank you, that's the word I was looking for. So for something like this, you've got the incident ray, so the light that's coming in. The angle of incidence is, in this case, it's always the angle between what we call the normal line. And a normal in math means it's the line, normal means perpendicular. 90 degrees. Yep, we've set it up before, I'll say it again. It's perpendicular to the surface, right? And so the angle of incidence, we call this theta sub with a little subscript I next to it. The angle of incidence is right there. So then your reflected light is going to come off like that. And the angle of reflection, we call it theta little r, is equal to the angle of incidence. Where things get a little bit weird is when you start to curve your mirrors. On an outwardly curved mirror like this, you might see this like on the back of a spoon, for example. Have you ever looked at yourself in the back of a spoon? You get light that bounces off at weird angles. Which is why when you look at yourself on the backside of a spoon, what do you see? Take those lights. Take those glasses off. What do you see, Manuel?
The middle of my face is bigger.
Yeah, your face kind of gets stretched out, and the reason you see your face all stretched like this is because the light. It's a function of the curve of that mirror. The light reflecting off your face and back to your eyes is coming off at this kind of stretched angle, and so it pulls your face apart. On the inside of the spoon, what do you see? You spin the spoon around. What happens on the inside of the spoon? Your face not only does it go real small, it goes upside down. And the reason for that is this. If you're far enough away, I mean, for those spoons, very rarely are you holding it this close to your face. You're holding it far away, and so you see it as inverted. Well, why is that? Because when the light comes in straight, it hits this curved surface. The angle of incidence is equal to the angle of reflection. And so you get, like this angle and this angle are supposed to be the same. This angle and this angle, come on, sketching this bad boy a little bit. This angle and this angle. So what's going to happen here? These light beams are actually going to cross. What was the top of your face, you see as being down below. What was the bottom of your face, you see as being above. And then there's going to be a point in the middle that's not, your nose is where your nose is. Maybe that's where the thing is level. And so what you're going to get here is you're going to get a reflected image. Sorry, I won't say that because it's all reflected. I'll say inverted. In this kind of mirror, you get an inverted image. This kind of mirror, you get a stretched image. Yes, Connor.
I heard if you're like really close to a really big black hole, the light or the black hole has
Not related to what we're nope,
Yeah,
nope,
but it
stop.
bends the
Stop.
light around
Stop.
the lost of black hole.
Stop.
Like you can see
Stop.
the
Hey.
whole image.
S-T-O-P. Stop means stop. Okay.
What is it?
The wave pulses are a little bit different, and this is where I really wish I had a giant slinky, and I don't. Yes, Manuel, take those glasses off, or I will take them from you.
If the mirror on the bottom is concave, what's the other one? The one in the middle?
Convex.
Convex. Why do you wear glasses? They're like
Not in my classroom, I don't.
Mavericks.
I don't care. Okay, so I hope I can. I had these videos. Where did they go? Okay. Here, this is the one I want right here. So, if you flip the page. I'm going to show you a couple videos here. We'll pause this. Come on. There we go. Oh, look. There it is. I'm sorry I paused it. No, you missed some stuff, but that's okay. So wave pulses are going to change whether or not it's, you can think of it, the fixed end, is it hitting a hard surface? Here you can think of it as it's actually changing mediums, which is interesting. What happens when it changes a medium is that some of it gets reflected, but some of it actually gets transferred on. And that's where we come to the concept of refraction. Hands up if you've ever heard of this term refraction before. Manuel, in what context?
Like going through something.
Yep, okay. Okay. Like a prism? Like a prism? Okay. Harshan, what context? Have you heard of refraction? Okay. Luis?
I heard about it when I was studying geography, the term albedo, that is like the sunlight reflection to the ground, but because like if the ground is darker, it will retain more heat. And
Oh, interesting. Okay. In that context? Connor?
Rainbows. As light goes through.
Rainbows. As light travels through moisture in the atmosphere, it does the same thing that it would during a prism. So if you have a white light that goes in, we understand white light to split up into a whole bunch of different colors. Well, why does that happen that way? That concept is refraction. We're going to talk about refraction as water waves, and then we're going to talk about them in terms of light, because that's where refraction really is more involved. Not really, because not in the same way. So as you've got, in water waves like this, let's say, so the waves are traveling like this, moving through deep water. As they encounter a shallower area, what happens to those waves? If you can kind of picture it, I don't know if you've ever been to White Rock, if you've ever been to the beach and the waves are coming in. If the waves are coming in at a bit of an angle, you can see this effect really, really nicely. As they get coming in at an angle, as they get closer to the shore, what happens to the distance between those waves? It gets shortened. Why does it get shortened? Well, it gets shortened because as the waves change in depth like this, the part that is shallower causes the water to drag. And so now you're introducing a source of drag. You're causing the water to slow down. And the water behind it is still moving quickly. So you've got water that's moving pretty fast, and then you got water that starts to slow down. The parts that are interacting with this new shallower area start to stack up because they've slowed down, but the guy behind it's still going fast, so he does some catching up, and then he starts to slow down when he interacts with the shallow water barrier, so you get the small wavelengths here. It's a little bit cumbersome to talk about in terms of water, but that's what's happening here. Refraction is the behavior as waves change from one medium to another. So in terms of water, it could be deep water versus shallow water. The wavelengths decrease as the water moves from deep to shallow. And the direction of the waves change as well, because as you're dragging on this whole thing starts to slow down, and so you get this bend in the water. Manuel, wake up. Notice, though, the frequency does not change. Because the waves were generated at depth, the frequency hasn't changed, but the wavelength does change. The waves are still coming at you at the same rate. They're just coming at you with a smaller wavelength and a slower wave. But the amount of time between each one is still the same. Since V equals delta, the wavelength times the frequency, because the frequency hasn't changed and the wavelength has decreased, that tells you that the velocity of the waves decreases as well. The really easy place to talk about this is in terms of light. So flip the page here. Let's talk about refraction in light. Refraction occurs when a wave changes direction as it enters a new medium. The change in direction is caused by the light itself changing speed. Now, I hear you. Was that Cohen? You said, but light is light? Oh, what about light bulb? Never mind. I thought I heard something different. So, some of you might say, well, but the speed of light is the speed of light. We know what the speed of light is. And that is true. There is a difference, though, between the speed at which something travels and the speed at which something propagates. The language there is different. What's happening when we talk about light slowing down, what we're actually causing, Niraj and Cohen, to happen is the light is still traveling really fast. We just put objects in the way of the light so that as it bounces between things, it travels the overall distance slower because the path is longer, not because the light itself is actually slowing down. So it's the idea of propagation speed versus the speed of light. Light still is fast. We're just increasing the rate at which the distance it has to travel by giving it a whole bunch of things to bounce around. So the interesting effect here is this idea of refraction. The change in direction is caused by the light changing speed. As light travels from air into water, what happens? Well, you've got the light coming in, and now we still have our angle of incidence here. We call it theta I. Theta I, the angle of incidence, again, is always between the normal line and the light ray. If this is air and this is water, this line represents the surface of the water. It's the medium that the change in medium happens here. The light is actually going to bend. It's going to slow down, which causes it to bend towards the normal line. And so in this case, we have our theta r right there. That r now doesn't stand for reflection, it stands for refraction. So that becomes our angle of refraction. As the light hits this new medium, its wavelength decreases and it slows down, bending towards the angle of refraction. How much the light bends is determined by the substance it is moving into, and actually on your formula sheet you'll see we've got a chart that outlines a whole bunch of these different substances and what's called the index of refraction. The measure of how much light will bend in a substance is called the index of refraction and is given the symbol N. If you haven't already, grab your formula sheet out. You'll see at the bottom at the front, there's a table of indices of refraction. So I need a new one of these. Good one. On the bottom on the left, you'll see a bunch of these refractive indices. So if your n is more, so air has an index of 1 because this is what our standard is. Light always travels through air. It's when light travels through other things from air into something else that it's going to bend. So if air has an index of refraction of 1, if n is more than 1, the substance bends light more than air does. If it is less than 1, the substance bends light less than air does. So larger n also equals more bend. An interesting, oh, it screwed up my picture here. That sucks. But an interesting effect is this. Yes, sir.
If light travels through air, or sorry, not air, but I mean like in space, is there 0 n?
In a vacuum?
Yeah.
That's a good question. Yes, it would be 0. That would be 0. An interesting effect from this is what happens when you look at an object underwater. So if you follow what's happening here, we think about, so light comes in from the sun, it reflects off of the objects. This is where the object actually is. And you can think here like you've got our normal line right here. So this guy right here becomes our angle of incidence, because when you see an object, you're not actually seeing the object, you're seeing the light bounce off that object. So if the light doesn't bounce off an object, you're not going to see it. So we have our little submarine down here. Light bounces off this object and it comes back up towards the surface of the water. Because water and air have different indexes of refraction. If you look at that chart, water has an index of refraction. We'll label it down here. N water is equal to 1.3 repeating. Let's write it as 1.333. And in this case here, because that is greater than water, it bends light more than air does. So when the light rather comes out of the air, what's going to happen is the angle of refraction is going to be larger because the air allows the light to bend less aggressively than it would in water. So then the opposite is true. As it leaves, it bends away from the normal line. And so you see the light coming in shallower than it left the submarine. What that causes your brain to believe then is that the object you're looking at is actually over here when it's not. It's right here. So you see the object right here. And I'll write this down here. The object appears to be here because the air has allowed the light to follow the path, a less restrictive path. So this has all sorts of interesting applications for those of us who happen to be fishermen or fisherwomen. Because if you see a fish right here, where is it actually? It's deeper and closer to you. And being able to compensate for that is important. Something people have had to learn how to do for a long time. One really easy way to compensate for that is to do what? What's a really easy way to get around this effect? That is effective, but ultimately terrible because you get in the water and the fish run away. Yeah?
Look straight above.
Get higher and more above, then the bend is less pronounced. Absolutely. If this eye is not here, the higher this eye goes, the lower the discrepancy between the angle of incidence and the angle of refraction. Yes, sir?
So is that why bald eagles and ospreys go high above to catch fish?
And drop straight down, yeah. Which is why people who would fish with a spear are going to do it from the top of a tall rock, as opposed to, or a heron too. It's why herons have such long legs and such long necks, so that they can look out and over and shoot straight down. Yes, Connor. That becomes an entirely different scenario. Yes, you could join them under the water, and then there's there's no change in medium. Absolutely. So, flip the page. When light waves pass from one medium to another, the direction, the speed, and the wavelength change. The frequency does not. When light passes from one medium to another, from a medium that has a low index of refraction to a substance that has a high index of refraction, the light slows down and bends towards the normal. So low index of refraction to high index of refraction. So an example of this would be like air to literally anything else. It slows light down, bends it in. So we'll say like n equals 1 down here, n equals, well, greater than 1. And we'll call this Ni, the incident index, and this n little nr, because we don't actually know what these things are, but we know that this is where the light is incident, and this is where the light is refracted. So we'll call it Ni and Nr in this case, instead of n water and n air. When light passes from a medium that has a high index of refraction to a lower one, it allows the light to speed up, and it bends it away from the normal. So here you'll have Ni being greater than 1, and here you'll have Nr equal to 1. So if you extend this idea, and the light is going fast enough, you will reach a point where the refracted angle would be 90 degrees. And what you get here, again, I don't know why my computer blew these things up. What you get is this. When the light comes in at this angle, we'll do this, where is it here? Right, I'll do it in green. It's this one right here. There's an angle called the critical angle. This one I've labeled here in green. It's hard for you to see in green. I'll call this theta I. When theta I is small enough, the light's going to bend out. But you can see here, as this angle gets bigger and bigger and bigger, this light ray is going to bend down further and further and further and further. And what you're going to get here is there'll come a point where called the critical angle, where the light actually doesn't escape. It travels along the boundary between the medium. As you increase this angle further, maybe is it on the next page? It is on the next page. Flip the page. So then label this one here green as well before you do that. This one, you get this critical angle where it bends along the boundary. If you flip one more time, as the angle gets bigger than the critical angle, we'll say this, for angle greater than the critical angle, if I could spell critical properly, critical angle, you're going to get something that looks like this. I'll draw my normal line. I'll draw my boundary here in blue because this effect is really cool in water. Let's draw this one here in red. Here I'll have this, I'll call this theta C, which is my critical angle. This is where the light's going to bounce along the boundary. For an angle that's larger than that, I'm going to draw it here in, I'll use lime green. As the light comes into that point there, what you're going to get here is instead of being allowed to escape and refract out, what's actually going to happen is the light's going to get bounced back in.
That's so cool. So if you're underwater, you're looking at
So you can see this happen in water. If you are at the right angle, if you look straight up, you'll be able to see the ceiling. But as you look further, try this the next time you go swimming. As you look further and from the bottom of the pool, as you look further and further, eventually you're just going to see the whiteness that is the surface of water. That means you're at the critical angle. And as you look further away, you get a larger angle. You're going to start to see things on the underneath of the surface of the water that's being bounced to you from what's happening over. It acts like a mirror.
that's what trippy.
It's pretty cool.
It's
It's hard to do for most people. This is hard to do because unless you're like actually good at holding your breath, by the time you're down there long enough and have focused yourself and you can actually play with this, you need to breathe so people go back up. Zaid, as you're doing your lifeguard stuff, take a look at it next time you're down there. I played with it for a long time. I'm a certified scuba diver. I did a lot of my work in pools. So I was able to stay on the bottom of a pool for literally hours because we have tanks of air on our back. And so I was noticing this was really, really cool. And you can watch people at the far end of the pool. Like I could see them normally, but I could also look at the surface of the water. I could see their reflection bouncing back to me from the underneath of the surface of the water. It's a really cool effect. So there's actually a really financially viable application to all of this, because it's not just water that does this, it's also anything that has a larger index of refraction than air does. An application of this is something called total internal reflection, where you get it to the point where, dang, it cut this thing off here. You get kind of a mirrored effect. As the light bounces in, again, you've got your reflection and refraction. Here, you get what's called total internal reflection, because the light is not allowed to leave. Here we are where theta I is bigger than your critical angle, whatever that critical angle is. If you apply that to cutting diamonds or various other gemstones, you get this really cool effect. If you cut the diamond such that the light coming straight in is going to hit the bottom of the diamond at greater than the critical angle, the effect that you create is that the light is not allowed to leave the bottom of the diamond. Instead, it bounces around inside the diamond for a while and then exits out the top. And so what you have here is, instead of just light bouncing in and out, you have all of that light going in, bouncing around inside for a while, and then leaving the top of the diamond. This is where you get those crazy sparkly diamonds if they're cut well. If they're not cut well, then it just escapes out of the bottom of the diamond and into the base that is the ring.
That's a sample.
Oh, thanks. I'll show those guys. And then you get, it doesn't matter, not related to optics. And then you get not that effect, and you get this kind of, it doesn't look as good. So, an application of total internal reflection. Another application of total internal reflection are fiber optics. So you guys, do you know what fiber optics are? Or do you just know that fiber is faster internet because it's faster internet? Okay, so what fiber optics are just glass tubes. So you get these glass tubes.
Oh, like glasses.
No. Okay, so diamonds are an application of total internal reflection. Another one of these things is fiber optics. And you might ask yourself, well, how do tubes of light allow for, the transmission of data? Why doesn't the light beam just, leave the glass tube? And the reason for that is, how you can bend it around places is the light. All you have to do to make sure light doesn't leave this tube is make sure it's entering the tube at an angle that's greater than the critical angle for that material. And so what will happen is the light will go in, the angle will be so large it'll bounce down, and we know the angle of reflection is equal to the angle of, reflection is equal to the angle of incidence. And so what's going to happen here is you're going to get this effect where, yes, it's a glass tube, but light is going to follow the inside of that tube because it's bouncing around at angles that are larger than the critical angle, creating this total internal reflection effect. So it allows you, instead of transmitting things at the speed of electricity, like electrons moving in wires, which is quick, but not as quick as transmitting information as pulses of light traveling at the speed of light. It's much, much faster. You can transfer a ton of data way quicker, which is why fiber optic internet has the potential to be so much faster than regular copper wired internet, which is what used to be around. Because this is traveling the speed of light, not the speed of electrons in a wire, which is really, really cool. So this was all of the theory for this, because I gave you a bunch of stories at the beginning of class. Tomorrow we're going to look at all of the math behind this, and that'll be the last lesson that we do. Yes? I do have the final review packages printed. For those of you who are going to be away or want to start working on them already, you can pick them up before you go. Luis?
There is something that is faster than light.
No. There is nothing that is faster than light. Actually, no, but that's okay. Okay, so there we go.